Yeah, now you can start. Vinayji, you can continue.
Okay, sir, no problem.
Thank you.
I continue. Okay. Okay, I believe everyone can see Microwind screen now. I'm sharing the Microwind screen. Okay, and from here we can start. Okay. So can you see the palette also? A long rectangular block on the right hand side. I'm spelling. Okay, good.
Yes, sir.
Because it was coming as a two separate windows in my Zoom sharing. So I just wanted to confirm that both of them are visible. Someone raised hand. No problem. You can keep your hand down and ask me the question verbally if you want. No, no problem. Okay. Okay. So just it's quite tight. Okay, so this is how what I've started. No need to follow through. Just sit dark and just keep your eyes on the screen so that you can just see and remember and follow through. So I will ask you to follow through. Okay, so there are two things to do in the hands-on. One is watch. Okay, so that means you will be just watching what I'm doing. The second thing is follow through. Okay, so when I ask you to follow through, so then step by step, I will move in a step of 10 seconds each. Okay, so it will give you ample amount of time to follow me as I'm doing here. So when I start Microwind, it opens in 45 nanometer technology. So I keep this technology as it is. I don't touch it because that will bring changes in your setup platform. So let's start today again making with a new inverter design. Okay. So yesterday we saw that we wish to make an inverter which can drive a high capacitive load. So let's say today also I want to do the same. Okay. So I just go to this palette, and on the palette you will see a transistor like symbol, MOSFET like symbol. You click on that. Don't follow through. Just watch first. Okay. Don't follow. So I do some math calculation. I came to know that I need to have 5 milliampere of current to drive that size. So you can micron size or lambda also you can make. So you can say that this is 22, no, 100 lambda, no, 200 lambda. Okay, but 200 lambda, it give me a 3.6 milliampere of current. Because 200 is quite big enough, and this big it will be. Okay, and I take the second time MOS generator. I select PMOS, and when I click on the Ximax, it shows me the current is 2 point something. So I make it 300. No, 350. It should be 3.6, right? Yeah, for 340 lambda, it is almost the same because I gave what 200, right? 3.6 for PMOS is 340. 3.6. I place side by side on the clipboard. I press the zoom button, and I just zoom through, so I can just see them closely. Because if you see the 3D view, you can see that they are the long set of transistors. Okay, with multiple number of wires. Whatever the cross sections, the cross you see are the wires. Okay. Now to make connection, I take the gate material and left click over here and drop the block. So that joins the gate. I take the metal one, join these two nodes. This much metal is good enough. Okay. Now I'm ready to simulate. I take a VDD supply for the PMOS anvil and VDD supply again for the PMOS, the second terminal. You just left click and just go to that location and left click again, and you will connect the ground like this twice. And now you take the clock signal and apply at the gate. Make it like 1 nanosecond low and 1 nanosecond high. Assign it and take the visible node and place it over here because this is what you want to see, S1. And take a virtual capacitor and connect over here and make it maybe 1 picofarad. Say okay. And just change the background color and press this play button to simulate. So thereby you can see that it is simulating and working at the rise and fall time delay of 154 and 157. They are quite very closely matched. So this is as good as having equal rise and fall time. So that goes very well, right? Any doubt on this? Okay. So this is it. So this is how it looked like. Okay. I'm using widescreen mode because as Zoom is sharing my screen, so what happens, both of them are capturing the screen. So it becomes, the refresh rate becomes very slow. So that's why I use the white one. It's more faster. This is okay. Okay. Now, if I ask you this question, can you give quick verbal answers because they are faster to get and understand? Where is my chat window? Right. Now, if I ask you a question, as yesterday, if I have a higher capacitive load, and I have to drive that load at high speed, what should I have more? Current, voltage, power?
Current.
Yes, right. Current should be higher. Okay, it's just like I have a bike and I want to go faster, right? I need to have a bike and I need to go faster. So I need a bike which will have a higher torque. Simple. I need to have a bike which has a higher torque. Okay, that's it. So is this understood? Now, how you get higher torque? Tell me.
By increasing the size of transistors.
Okay. And for the engine, what do you do?
Increase efficiency.
Ouch. No. I want to increase the torque of my bike selections. I'm like, so what shall I do? What change you notice in the bike? And lower torque bike and higher torque bike, what is the difference?
Engine size.
Size of
Yes, engine
sir.
size. Engine size. That is cubic capacity or the cylinder volume, right? Okay, so engine size is more. So in case of inverter also, if you need to have a transistor which can deliver more current, so you need to increase the width of it, isn't it? You need to increase the width of it. Now, if I ask another question, so engines are all same. You talk about car engine, bike engine. Why the car can carry 4 people? Because it's 1200 cc engine, right? 1200 cc, 1000 cc, or maybe 1400 cc, something like this. These all cars have standard small size car has, isn't it? So size of the engine, increase the size of the engine, and then you get the motor. Now, if I ask you that, how big this 100 cc bike engine is this much? Yes. 100 cc bike engine, this much big, right? So what is that size? This is the size of that cylinder, the piston. This is the volume of the piston on inside the engine where all the energy is being produced, right? Where all the energy is being translated. Okay. So the 100 cc is this much. Okay. Now I need a bigger bike. Okay. So I need a 350 cc. So I will have this much size engine. And this you must have seen in Royal Enfield Bullet. bike, you have 500 cc engine which are this much big, 350 cc, right? You need bigger, powerful bullet, 500 cc, and this is also what you have seen, right? Okay. Now, what is there? They are still single. This one. Now, if I ask you, have you seen a 1200 cc engine in the bikes, the cars? Have you seen it? Ouch. Someone says, no, you have not seen a 1200 cc or 1000 cc bike. Maybe you're not in Bangalore. In case of cars, you have seen a 1200 cc engine, right? You have seen a 1200 cc engine. So if 100 cc is this much height, in height, this much, 350 cc is this much. So don't you think that 1200 cc would be this much? Isn't it? 1200 cc would be yo big. Isn't it? The piston, the cylinder would be that big. So have you seen a car with a bonnet so big in height? Have you seen?
No, sir.
No, you have
No,
not
sir.
seen it. So okay, you may argue that sir वो कार है ना height में नहीं होती है, उसको इंजन को 90 डिग्री टेढ़ा करके ऐसे लगाते हैं, horizontally. But then you have cars like 3000 cc, isn't it? तो क्या वो मतलब उनकी चौड़ाई तो कितनी हो जाएगी? I mean, they would be 2 meters wide or 3 meters wide. So good. So I get good answer that yes, number of cylinders are more. So the volumes are divided. So you have to keep everything in a good aspect ratio, because you can't have a 1200 cc engine in like a single cylinder. You can't have that, because the geometry of the size, geometry of the engine will not allow the designer to fit inside the vehicle. It won't be possible for him to do that. ओके आप इमेजिन कीजिए आपके पास 1200 सीसी का बाइक है एंड उसका सिंगल सिलेंडर है और आप यहाँ बाइक पे बैठे हैं और आपके सामने एक पिलर लगा हुआ है इतना ऊंचा. Can you drive the bike? No, you can't. Okay, so even you see Harley Davidson bikes which has 1200 cc or maybe 1800 cc engine, they have 2 cylinders. Okay, they have 2 cylinders, V shapes. Okay, so they are fitting like this, so to accommodate inside, so they move in the V shape, and in the central area the rider can sit, and in the central area you have the engine, the fuel tank. Okay, so this is how they work. So even in the car, if you have 1200 cc, they are divided into 4 cylinders, 300 cc each. So you have 4 cylinders, they are connected in parallel, their all power energy is transferred to the same shaft, so that the maximum amount of torque can be produced by the engine. The same logic we have to think over here. And look at this inverter, the size of the inverter. It is not good in a aspect ratio. Okay, it is so heighted that for any designer it might be difficult to fit through. Okay, so what you can do is that you can design an inverter which has a good aspect ratio. So I just select NMOS and reduce the height to maybe 100. Okay, and here I say number of fingers are 4, and height is again I adjusted 3.6 milliampere I was getting, right? Okay, so for 52 lambda width, because this is what we are doing now, 1200 cc engine divided into 4 cylinders, 300 cc each, 4 cylinders. So 300 cc, 300 cc into 4, it will give you 1200 cc. Okay, the same we are doing. So it's a 52 cc width and 4 cylinder, 4 number of fingers. Okay, it will give me the same NMOS current, which is 3.6. Place it over here. Okay, then again go to MOS generator, select a PMOS, and it is, I just increase the width to maybe 66, 82, maybe 90. So for 86 lambda, I'm getting almost the same amount of current by the PMOS transistor, and I just place on top of this one. I change the color and zoom the central area. Okay, so this is how he generates it. Maybe I just don't zoom the entire one. Can you see this one? So number of channels, yes. Number of
Yes, sir.
fingers, number of channels, yes, number of channels. To some extent, you can say that. It's like I can't see this. Okay. So what it does, you have he generates like this. Multi fingers are like this. So this is a common point. You know, drain and source are shorted to each other, right? So here you have a drain. This is drain source. Okay, sorry, source drain. Right? So there is a common point, isn't it? There are two transistors. Is this okay? So now if I have to use these set of transistors in series, so what I will do, I will apply the input A over here and I will get the output Y from here. And I will apply the input 1 and input 2 at the gates of it. So they will work in series. Is this okay? Yep. But if I short these 2 points and I give the same input to both gates and I short the endpoints of these 2 transistors and I give the input A over here, so I can have the output Y from here. So they become in parallel. They become in parallel. Okay. So it was just like having something like this. Something like this. Only, you know, the visually they are different. Okay. So this is how the NMOS is. This is what the NMOS is. I just take the print screen and maybe talk a little bit on it. So you see this one. This one is one transistor. So you have the input over here, drain, and output over here, source. Now this is the second stage transistor. So here he has a drain and source shorted to the first guy. Okay. So if you want to make use of this 4 transistors, these are 4 fingers, 4 transistors. So if you want to make use of in this transistors in series, so you apply the input on this node and take the output from this node. That's it. Okay, and you apply inputs like A, B, C, D on this 4 gate materials. Okay, but if you want to make them in parallel, so what to be done? Okay, so I will short these all 4 gates. I will short them. Then I will short the nodes which are on the top side. Okay, and I will short the nodes which are on the bottom side. So this will become in parallel.
Sir, it is not visible.
Ouch. Okay, you shall not. Sorry, I opened my paint area and I started talking instead of looking at the chat box. Okay, so these are 4 transistors which are of 4 fingers. So this transistor is the first one. So you have drain and this point is source. Okay, so if you want to make this in series, so you apply the input from here and take the output from here. Okay, giving the inputs like 1, 2, 3, 4 at the gates. Okay, but if you want to make them in parallel, so what you can do? You can short the gates. You can always short the gates. Then short the endpoints of all these 4 designs, 4 transistors, and short the topmost points. I mean, only the top points. Don't short everything. ऐसा नहीं कि सब कुछ short कर दिया, इसको भी short कर दिया, नीचे भी short कर दिया. No, 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 no. Don't do that. So only you see that this metal lines are coming a little bit outside than the alternate one. Okay. So you have to short only that top side. Okay. So this will become in parallel. Okay. So, okay. So what I do is I take the palette, I take the metal one and short the bottom side. So you can see that the sources become parallel, and the NMOS also I short the top side. The same stuff I do for the PMOS. I short these bottom side. Okay. Which drain, which source for MOSFETs, it doesn't matters because they are unipolar, bidirectional device. So anything can be source or drain. Okay. So I've shorted the PMOS side also. Then I can short the gates also. I just take the gate material and short these 2 points and short the PMOS and MOS and like this. Now only the connection of the PMOS to the NMOS is remaining. So I take the metal one layer and short the entire block, middle block. So this is my output. So I take a visible node, connect to this guy and call it S2 is okay, no problem in that. Then take a VDD supply, put it to the N-well, VDD for the PMOS, the other side. Okay. Then ground to the NMOS other side. That's it. And a load, a capacitor load of 1 picofarad, because this was the load I connected to the first stage of transistor. And then I just simulate. I didn't give a clock. I take a square clock and apply at the gates. So same 1 nanosecond speed. Didn't I connect it as 2?
Vinayji, they are finding some a little bit fast. Can you go a little bit fast, slow?
Okay.
There is some chat message. You can see that.
Yes, I saw that just now.
Okay.
Okay, I think I connected VDD on the top side. The VDD is this one. So I connect the VDD over here. Don't worry, I will just ask you to do follow through. So just I'm checking. This is listed as not visible, or I think this one got shorted. So I think this one went wrong. Yeah. So this is the outer side, the inner side. Yeah. So the metal layer was this one and the second one. Yeah. Now we should see it. So this is your S2 output. This has the same performance, 150 picosecond, same as the previous one, same to same. Okay. And if you look at the dimensions, okay, so you can see the aspect ratio is different. It may have the same area, but aspect ratio is different. It's just like I come to you and tell you that, sir, mere paas I have a very good plot to sell you, and you can make a very good bungalow on it. And you ask me that, okay, what is the dimension of that plot? So I tell you it is 200 by 10. So I mean, like 200 by 10. You say yes. That's it. So you have to buy this. It's very good plot on the main location, etc., etc. Like that, all the benefits I try to sell you. But then you think that 200 feet by 10 feet is the size of the plot. Will you buy this for your bungalow? Probably not. You will not buy it. Now you tell me why. You think on it, because there is no technical answer to it. Okay. Uh, but if I come to you and I tell you that I have a bungalow plot to sell, and these are the features of it, and you ask me the dimensions, and I tell you it's 40 by 50. Okay. So there is a high probability that you will buy it, because 40 by 50 is a good aspect ratio, and you can build something constructive or creative on it, instead of having a 200 by 10 size of the plot. Whereas area wise both are same. Okay. But they are differ in the aspect ratio. Okay. So this is what it is, that the second inverter design is easier to fit as compared to the first one design. Okay. So I just save the file somewhere on the desktop in the course, let me say inverter one. I just save the file as inverter one mask file, and I just share this with you. Okay. Now maybe you can just follow through. I just make one inverter for you guys, and you can do the same inverter as follow through. My home will be a train. I mean, my home will be a train means like, yes, your home will be a train. Yeah, definitely 200 by 10 is a train. Yes. Okay. So let's do a follow through. Now you can open your Microwind software. I give you 10 seconds to do that, so that everyone can get time to do this. Just open Microwind software. Let it be like this. Don't click anything. Don't move further. I'm sharing the mask file, which I just made right now, so that in case someone wants to refer it, so you can just open it and refer to it. I believe now I will move at the pace of 10 seconds. Okay. So every 10 seconds I will go to the next step. So you have to do your step on 10 seconds. Okay. So I just open the clock and the time. Yeah. So I believe till now everyone has opened Microwind software. Okay. And everyone is ready to make inverter and do this. We will do a finger-based inverter. Okay. 1 minute. Okay. I'll just wait a few seconds more, maybe. Rest of the people, I believe everyone has opened Microwind software and ready with your mouse. Okay. So let it be in the default 45 nanometer technology. We will not change that. And we just move. Okay. So on the palette, you see this is a palette. On the right hand side, you must have found it. Or it can be opened by pressing this multicolor first button on the right hand side of the toolbar. Okay. You see an option for MOS generator. You click on this MOS generator. Okay. Specify the width of the MOS as 20 lambda and number of fingers only 2 or maybe 3. Only 3. Don't do 3, more than 3. Okay. Put the width as 20 lambda, length as 2 lambda, number of fingers as 3. So it should show you almost the same amount of current, 0.989 milliamperes. If it is showing more, because probably of the Bangalore, the southern weather, in change of weather, it gives you different figure values. So that's okay. Okay. So just click generate device and place somewhere on the clipboard. Just left click and it should be dropped on your screen. Is it done? It's showing 1.2.
So can you please repeat?
Okay. From start?
Yes,
So
sir.
you must have opened Microwind software.
Yes, sir.
Can we okay. So click on MOS generator. Those who have done it, just stay there. Is it opening? MOS generator. So just give it the width as 20, length as, let it be 2, and number of fingers as 3. Click on NMOS. I mean, it should show 0.989. Okay. If it is not showing 0.989, so that means either you have changed the technology. Go to file, select foundry, and it must open in the C program files, Microwind. I think it should open in your folder, don't worry. I mean, it opens that folder. Select default file. Select the default file. It should show it's a Cmos 95, 45. Or otherwise you can turn off Microwind and start again. Shall I proceed for the rest of the people?
Sir, I'm not getting.
You just close the Microwind.
Yes, sir.
Now start again.
Yes, sir. Started.
Can you see the palette?
Yes, sir.
Click mouse generator. Have you clicked mouse generator? Hello? Hello?
Yes, sir.
Okay. Just type the width as 20, length as 2, and number of fingers as 3.
Okay, sir. Thank you, sir.
How much it is? See? 0.989. Okay. Now you have placed the NMOS transistor, so you can instead of don't click on zoom all, you just click little bit minus and press the arrows to adjust on the bottom side of the screen. Keep the NMOS on the bottom side so that when we generate PMOS, it can be placed easily on top of it. We don't feel any alignment problem as you are doing for the first time. So it should be there. Sainag and G Tanya Shri, I would recommend to close the Microwind and start it again so that it opens from the default rule file. Probably your rule file must have changed. Yes, it should be in Lambda, not in Micron. Okay, so, and even though, yes, if you have got 1.2, no need to set default, you just close the software and start again. It should open in the default technology rule file. Okay, and even though if you're getting higher value, don't worry, it's okay. It's definitely okay. Okay. Again, click on MOS generator. This time select PMOS. This time select PMOS, and you will see that it shows a lesser current as compared to NMOS. Instead of 0.989, it shows 0.582. So we try to increase the lambda and try to match it. So it is 32 maybe, or maybe 33. Yeah, 33 is good. So you can set the width of the PMOS in lambda. You see the units is lambda, not in micrometer, because if I set micrometer, the things may go wrong. So in lambda, it is 33 lambda. Okay, length is 2 and number of fingers are 3. It should be PMOS. The current should be around 1.002 milliampere. You click generate device and you will see that it shows a shadow ghost kind of effect, and keeping a good space between both transistors, you try to align the gate rectangles and left click. Just keep on increasing till you get the matching value with this. Generally, it is like twice, 1.8 times of the NMOS value. Then you can click zoom all and you should see both PMOS. Even though you're not getting the same values there, no problem. You just generate a PMOS, because today we are just learning the steps how to making an inverter. We are not trying to make a perfect inverter as of now. We are just trying to learn the steps. Okay. It's just like हम पहले एक रोटी बेल लेते हैं, जरूर नहीं है वो गोल बननी चाहिए. It should not be a circular. We are just trying to make chapati. On the first day, it's not necessary to be a circular. Okay, don't worry. You will eventually make perfect circular one with 5.4 radius. Okay, you'll learn it. So if you have these two PMOS and MOS, now let's make connection. So you can click on the tin gate on the right hand side palette. You will find the red color, first red color from the bottom, which is mentioning tin gate. Okay. How to delete. Instead of, I will ask you to start from the scratch. I will not ask you to delete, because making from the scratch is more faster instead of deleting and making any further mistakes. This is what my experience says. So delete, I will go very slow so that you can catch us. Okay, just generate a Cmos, NMOS, and try to place on the clipboard. Okay. Now let's proceed with making the gate connected. So click on tin gate and left click and release. Keep left click pressed and draw the rectangle till you find that these red blocks are connected to each other. You do this. You are getting huge PMOS and NMOS. Maybe you can take a print screen and send me later so that I can see that what went wrong. You can just click zoom on. That's okay if you're getting huge one. If you're getting big PMOS and NMOS, no problem. Do one thing. Just go to MOS editor and make sure that the unit is set to lambda, not micrometer. Set it to lambda, please. Maybe because of that, because you are giving 22 micrometer size of the transistor, and it must be going beyond the size. Okay. So set the unit to lambda so that our all calculations between me and you are of the same level. So I believe the rest of the people have joined these gates. Okay. Now with the same gate, I mean tin gate, click on tin gate again and just draw a horizontal line like this, a horizontal block. So what will happen? All the gates are shorted. So technically, if all the gates are shorted, it's a kind of inverting logic, because the same input will go to all transistors of PMOS and all transistors of NMOS. Okay. I believe everyone must have done this.
Yes, sir.
Okay. Now you take the metal one. Okay. Now this you have to be very careful, because you have to draw the blocks very precisely. If you make any mistakes, then probably other side of the metals may be shorted. So click on metal one, and you see the PMOS, the two nodes are coming out or almost touching the anvil. You just draw a block and join them, and the block should extend to the two nodes of NMOS in which the metal was extended, which are coming a little bit outside. Don't go further below than this. If you go further below than this, it will short the other node of the NMOS. This is a very important step, guys. So make sure that you draw the block correctly. I'm holding my mouse so that you can also follow through the same. And if you want, you can extend, or maybe let it be like this only. So it should look like this. I believe everyone is able to do this. Not that complicated. Okay.
Yes, sir. Yes.
Now click on metal one again, metal one. So what you have done is you have shorted the top side of the NMOS and PMOS transistors. Now you have to short the bottom side of the PMOS and NMOS transistors also. So you click the metal one again and draw a block on the bottom side of the NMOS. Okay, draw a block on the bottom side of the NMOS like this. Can you see a dotted line, a shadow mode, and release your left click. So it will make like this. Everyone has made this? Hello, everyone has made this?
Yes, sir.
Okay, great. Now you repeat the same stuff for the PMOS also. You click metal one again and short the top side nodes of the PMOS. So you start drawing a block just outside the anvil and draw a block like this on top of the NMOS, sorry, PMOS. Okay. Now I release my left click, so it makes a block over here. That's it. And our inverter is ready to simulate. Okay. Shall I proceed?
Yes, sir.
Okay. Now you take the VDD supply, left click on the VDD, and very carefully on the corner of the N well, you can left click again. On the corner of the N well, the green one. So it is placed on the N well now. So now your N well will be biased, reverse biased to the VDD. Okay. Then you click again the VDD. You take the VDD again. Only VDD, don't take the high voltage one, which is just next to it. Just next to it is a high voltage. So what happens? Many of the students apply high voltage. So the inverter do not perform perfectly. So click the VDD again, and this time left click on the leftmost node of the PMOS. This one, this side, this side. Okay, left click over there. So it should apply VDD to the PMOS top terminal. Okay. Now you take the ground and apply to the NMOS bottom one terminal. This one. Left click over there, and the VSS is connected to the NMOS bottom side. Okay. Should it touch
So 1
polysilicon?
picofarad.
Yes, we are coming to it. Now take a square clock. You see a square clock? Take the square clock and drop it on the red body. The red body you can drop here on the bottom NMOS, this corner where the red body is absolutely clear and no one else is touching, so that you don't make mistake. Keep it centrally located. Many of times students apply on the blank location. So it opens a window like this. You can make the time low as 1 and time high as 1. Nothing else. Make sure you only change these two values. Only time low and time high. Don't touch the rise time and fall time. Because many of times students apply 1, 1, 1, 1 everywhere. So that will make your rise time also slow. So make the time low as 1, time high as 1. That's it. And assign it. That's it. Okay. So your clock is applied on the gate terminal. That's it. Then you take a visible node and place it on this output node, this one, because that is our output node. So you place on this one. And it will say that I will name it S1. Just say assign, no problem. I believe everyone must have done till this now. Now you can click simulate.
Sir, last step.
Sorry? You lost something on the last?
Yes, sir,
So,
last one.
yeah, so you on the palette you see a visible node is there, an eye-like symbol. It looks like a visible eye,
Yes.
open eye. So left click
Yes,
on
sir.
this one and left click on the node where you want to apply this node. I mean, you want to observe the node. So any node you wish to see in simulation, you have to apply a visible node to it.
Yes,
Okay.
sir, done.
Now you can click simulation. So you should see something like this. If it is not visible, you can increase the time scale to 5 or 10 nanoseconds. And it should show something like this. Now, I wait for the students who will say that, sir, nahi chala, nahi chala, nahi chala. I can't see this. Anyone who is not getting this kind of output? DSS is on the NMOS other side, on the bottom side, this one. Good. So people have started getting simulation output. So this is how it is there. You just run simulation, you should get it. Run simulation and it should show some square waveforms. Anyone difficulties, you can just voice chat. That's better. Yeah, value of VDD is always constant, obviously. VDD is always constant. It's like 1.2 volt or 1 volt, whatever the VDD is working on.
Sir, I'm getting polarized N-well to VDD, sir.
Sorry?
Morning. I'm getting polarized N-well to VDD.
So yes, you say yes, polarized to VDD, safe. It must be mentioning safe. So your VDD, you have not connected VDD to your N-well. So you have to bias, reverse bias the N-well also. So you have to take a VDD and connect it to the N-well also. Okay, you must have missed it. Ya to it must have placed on the black screen or it must have been placed at other corners. So that's why the issue. And those who are getting the output, so you can add one more thing to the output, that you can take a virtual capacitor from the palette. You see there is a capacitor like a symbol on the palette. So you left click on the capacitor and place on the output node where your output label is there, which is S1. And make this as like something like 0.1 picofarad, 0.1 picofarad. And if you simulate again, so you should see the delays also now. I mean higher delays like 54.7, 54.5. So that's good enough. Are you getting this? So I got one yes. So shall I assume that everyone is able to do this? I'm sharing these mask files so that in case you want to open and see what went wrong or something is troublesome in your design, so you can always refer these design which we have just made and perfect. Okay. Capacitance 0.1 picofarad, 0.01 picofarad, something small value. Don't keep it too high, otherwise it might be loaded too heavily. Okay. So I would recommend that you guys do. You can repeat the experiments. Okay. I just type it on my screen first and.
Vinayji, today they are
Yes,
going
sir.
to do the same assignment at home.
Yes, I'm writing 2-3 assignments for the inverter.
Okay, 2 assignment you are giving. Okay. If the student completed, just say yes. If any of the students are finding difficult, please get back to us again. Okay, great, done.
Just a second now. I'll just make something and then we close it for the day. I'm just writing a couple of assignments for you so that you can work on them during your weekend. Okay, so I just share the text file with you guys. So these are all inverter based, nothing complex or complicated. So you can do this. These are day one assignments. Okay. All inverter flavored. So it's the same strawberry flavor. You have to get it. Try to make it as many. Can't see them fully. Okay. What like? I've shared the text file. So I think they're all written over there. There might be a spelling mistake. There is only crossover voltage is C course. That's it. You didn't get the file. Oh, sorry. Did I? But I have shared with everyone. No, got it. Otherwise, I just share it again and also paste it. Okay. So you have to design an inverter with a crossover voltage close to 0.25 volt. The fourth one is you have to plot a DC curve voltage versus curve voltage plot of the inverter. You have to observe the biasing point, which is also called a quiescent point or the crossover voltage of the inverter. Okay. Then you have to design an inverter with a crossover voltage close to 0.25 volt. Okay. That's it. So we meet again on Monday.
Students, don't do like, whatever
Okay, guys.
you do it. And,
so maybe you can create that folder drive or that
yeah,
file
I'm
we were
doing it
talking
today.
about. The
Yes.
student ask questions and maybe write somewhere and I can verbally reply all of them.
Yeah.
Okay.
Students, one more thing, don't do that, as like, what you do it at a blue book, looking at a blue book and just copy it. See, try to do your research. See, you have a lot of option to do it in this software, play around. Okay, and when you do one design, actually you can keep adding and deleting some of the features and specifications. Okay, so that you can really feel that what is happening in that particular circuits. See, even at your college also, like when you do your basic circuits experiments also, when they say actually the resistor to be added, see that actually they know what if they're given around 300 ohm resistor, so just put that 400, 360 or 220 ohms resistor, then what happens? Just see that outputs. So by looking at changing some components on resistors and capacitor, you can feel a lot of circuit difference. Okay, see, if you don't do that, you will be doing only, it is verification of your experiments. You need to do a lot of experiments. Okay, so that's what actually the usual engineering lab study. Okay, that you need to to do that. Okay, so thanks for the day. Okay, we'll catch up on Monday and we'll intimate you that dates time.
Okay, sir. Bye bye.
Thank you.